Hello, in this video we're going to talk about chemical reactions for propulsion. So any chemical reactions that are involved in different propulsion processes, which would be like a rocket or a jet engine or anything like that. So what is happening in those engines and rockets? We have combustion, which is simply a fuel plus an oxidizer, which converts into certain byproducts and then your energy. So that's in simple terms. So one simple example would be carbon monoxide plus oxygen plus equals converts to carbon dioxide. But now as we see in this equation, we have on the left side, we have 3 oxygens. And then on the right side, and then 1 carbon. And then on the left side, we have 1 carbon and 2 oxygens. So this is not a balanced equation. So we want to balance it. So this one would be simple to balance. So we have carbons. So we can put coefficients in front of these elements here. So we have CO plus alpha O2 converts into a mu CO2. So these are just coefficients that we can place in front of the reactant, the oxidizer here, and the products. So now we can compare on the left side. So we can compare the carbons. So as we saw here, we have 1 carbon on the left already and 1 carbon on the right. So you have 1 carbon equals mu. So 1 carbon here, C1, we could say. So mu times 1 just equals this mu, so we know that. So now compare oxygens. So now we have 1 oxygen here plus, we need to multiply 2 times alpha, which then equals 2 times the mu. But we know the mu equals 1, so this converts into 1 plus 2 alpha equals 2. Do some quick algebra. We got alpha equals 2 1/2. So now putting these coefficients back in front of our equation. U equals 1. So we could leave it like that now that it's balanced. But if we want to, we can multiply everything by a 2. We have 2CO plus O2 converts into 2CO2, and that gives it using whole numbers. So this is what we could consider a stoichiometric reaction. This is a stoichiometric reaction, which means that there's no fuel or oxidizer in the products. So as you can see, all the fuel, all the oxidizer converts into all this CO2. There's no leftover carbon monoxide on the right side, and there's no leftover oxygen on the right side. So now here's our general combustion reaction equation with air. So we have some type of our fuel right here, and this is our air, and then these would be our products: carbon dioxide, water, and then nitrogen. And so this is a standard air. So this kind of shows you that there's 3.76 times more nitrogen in the air, the atmosphere, than oxygen. So that's where we get the 3.76 times N2. So we could easily balance this. So X, Y, Z are constants. So that's be associated with the fuel. So we can analyze carbons by saying X equals the mu, because carbon here, 1 carbon here. Hydrogen, Y equals 2 times nu. 2 hydrogens times the nu right here. That equals hydrogen on this side. No more hydrogens on the right or on the left. We have oxygen, Z plus 2 alpha, 2 times alpha, equals 2 times mu plus 1 times nu. Okay, and then nitrogen, we have 2 times 3.76 times alpha equals 2 times gamma. Now this is easy to solve because we have 4 equations and 4 unknowns. Because we know x, y, and z, we're trying to solve for this alpha, mu, nu, and gamma. So now here's an easy equation to write this out just in terms of x, y, and z. So if we know x, we know y, we know z, we can easily plug it into this equation here and balance our equation. So let's do an example right now. Let's say we have propane, which is C3H8. So that means that our x equals 3, y equals 8, and our z equals 0. So we can write this as C3H8. We're not going to include the oxygen because we have none. Plus our x is 2, or x is 3, plus 8 over 4. O2 plus 3.76 N2 converts into x would be 3 CO2 plus 8 divided by 2 H2O plus 3.76. X is 3 plus y over 4, 8 over 4, N2. All right, so then solving all this, we got C3H8 plus 5O2 plus 3.76 N2 converts into 3CO2 plus 4H2O plus 3.76 times 5 N2. So now quickly let's just check and confirm that we have the same number of oxygens, hydrogens, and nitrogens on the left as we do the right. So we can compare carbons. So we have 3 here, no other carbons. We have equals 3, no other carbons on the left. So that checks out. H, we have 8 here, which equals 4 times 2, which equals 8. So that checks out. Now we have oxygens. So we have 5 times 2 right there, which then equals 3 times 2 plus 4. So that would be 10 equals 10. Checks out. And now we have our nitrogens. So we have 2 times 5 times 3.76, because 2 nitrogens here times 5 times 3.76 equals 2 times 5 times 3.76. That checks out. So we have stoichiometric equations, but we also have non-stoichiometric reactions, which mean that there is an excess of fuel or an excess of like air, oxygen, whatever the oxidizer is. So this can be broken up into fuel lean and then fuel rich. So the fuel lean means excess air or the oxidizer, and fuel rich means that there is excess fuel. And you hear this, when you talk about like rocket engines and stuff like that, you often hear like, oh, this engine runs fuel lean, this engine runs fuel rich, and it can lead to different characteristics. But basically, fuel rich makes sense, excess fuel, fuel lean, there's like less fuel, excess air, or an oxidizer. So that can be written out. So this is a general equation for methane. So fuel lean here, we have so the left side stays the same. We have the fuel and the oxidizer converts into CO2, H2O, and then N2, but the difference is there's this excess oxygen term here. So that is our excess air. But then our fuel rich general equation for methane, we have same on the left, CO2, H2O, we have excess fuel on the right hand side along with the nitrogen. So unfortunately though, when this is the case, if we just know the reactants, we cannot, sufficiently balance the equation because we have 4 equations but 5 unknowns. So we have carbon, hydrogen, oxygen, and nitrogen, but we have 5 unknowns. We have alpha, mu, nu, gamma, and a zeta term. So we need something else to solve this equation, and that is the equivalence. So we need our 5th equation. So our equivalence relationship is psi equals F over A, so this is our fuel to air ratio, divided by the fuel to air ratio of stoichiometric. Okay, so if greater than 1, that means it is fuel rich. So if this is greater than 1, this value is greater than this value. So fuel rich. So the larger the fuel to air ratio of the fuel rich, greater than the stoichiometric fuel to air ratio. If psi equals to 1, that is just our stoichiometric. And if our psi is less than 1, that is fuel lean. Okay? So now that we have that, we can write these equations for fuel rich and fuel lean in terms of the equivalence ratio. So we have our equation for fuel rich and our equation for fuel lean. So all we need to know is our x, y, and z. So for methane, it'd be 1 carbon, 4 hydrogens. And then if we know our equivalence ratio, so if we know the equivalence ratio, we can pick which equation we need to use, and we can plug it into that equation. So if I said, like, let's say we have, let's say ethane, which is C2H6, combustion with an equivalence ratio equals to 0.8. What does that tell you? Equivalence ratio less than 1, therefore fuel lean, and then we have our x and our y. But let's say I said ethane, equivalence ratio equals 1.2. That tells you fuel rich. Use your fuel rich equation, plug and chug, and you can balance the equation pretty easily.